Alright, we're going to try this and see if this lets us use the pointer options as it does. So we are going to do a quick, real quick demonstration of how to do an open flow problem to determine interior pressure at any point in the system if in fact you know the flow rate. You would know the flow rate by sticking a bucket or determining the velocity in the area on the outside downstream end. So I'm going to sketch one up here, ballpoint pen. Here's a reservoir. The theory of a reservoir is that no matter how fast the water is flowing out, the velocity through the reservoir is zero. We're going to call that point 1. It goes down through some pipe which has a length L. If you remember your plan length, I'm going to make that a length L. It comes out with some Q here and some area. And so you know that velocity equals Q over A. So you need to get everything in the correct units. Alright, so this needs to be in cubic feet per second. That needs to be square feet. That gets you feet per second. Alright, here's the basic theory to this. Except for the fact that energy loses a little bit at particular spots where it just has to get in. That's an entrance loss there. And a few other spots. Generally you're losing energy consistently without the system. You start here and realize that if it has three types of energy, first off I'm going to apply a datum there. Very often let me apply the datum right there at the center. That makes it easier. That makes this at height h. Alright, so if we apply our datum right there, so we're going to just show you where x and y is there. If you apply our datum there, we're at height h. Well, it has elevation energy h. It has no pressure energy because this is a free water surface. So pressure plus P over gamma, that's equal to 0, plus velocity squared is equal to 0. So that's the first h. The second one is point number 2 at this exiting stream. It has no h, it has no pressure. Those are not x's, those are crossouts. But it does have a velocity squared over 2g, right, which you can calculate based on knowing its flow rate in its area. And then some head loss did occur. And here's what finally graphs out when you do that. You know that the energy grade line, which is the sum of those three terms, EGL, goes through the free water surface and it goes through a velocity head here. One velocity, that's the total amount of energy there, which is one velocity head over the datum. And here's the total amount of energy there. We should see whether this will draft a straight line. It won't. And then, in fact, what you can realize also that the hydraulic grade line goes through the point of exit and it is parallel to the energy grade line. So that's a real rough, let's see if that doesn't help. Alright, so we're going to see how this graphs out. We'll try this again at school. But the fact is, here's your steps. If it's a free-flowing system, one pipe size, it is a very straightforward problem. You assume that the energy grade line begins at the pressure and it has a value of the elevation plus the pressure. You know that it ends up here as the elevation plus the velocity, and it's a straight line between the two. You then can draw a parallel line through the exit. That is the hydraulic grade line. And from that, you should be able to determine a lot of questions about pressure at any one point in the system. Usually these pipes go up and down and the like, and so those energy grade lines are a lot more significant when you think about that. Thinking about the pressure being described by the distance from the hydraulic grade line to the elevation line. Alright, let's see how that works. And show.